The world's largest and most powerful space telescope has revealed unprecedented views of Jupiter.
In the vast expanse of the universe, humanity's enduring curiosity has driven us to probe its enigmas, forever reaching for the distant stars. However, just when we believed our cosmic exploration was exhaustive, a new era unfolded with the advent of the James Webb Space Telescope. This colossal observatory marks a transformative phase in space exploration, propelling us into uncharted territory. As the telescope embarks on its historic voyage, it has stumbled upon an intriguing revelation: unidentified objects scattered throughout the cosmos. These enigmatic discoveries baffle scientists and astronomers globally, sparking questions about their origins. Could they be remnants of ancient civilizations or phenomena that transcend our comprehension? Join us as we explore these mysteries and uncover the fascinating history and groundbreaking discoveries made by the James Webb Telescope. Kepler's intriguing dance with illusory planets. The James Webb Space Telescope just detected 755 unidentified objects arriving from another solar system. However, this is not a recent occurrence in the annals of astronomical observation. You see, throughout the history of our pursuit of celestial knowledge, there have been instances wherein new celestial entities seemingly manifested within our solar system. However, these discoveries did not always align with our initial expectations. One of the most renowned examples of such occurrences is associated with the Kepler mission, an audacious endeavor aimed at unraveling the enigmatic realm of exoplanets beyond our solar boundaries. Armed with its remarkable capacity to discern the most subtle fluctuations in starlight, Kepler's research initially uncovered a multitude of potential exoplanetary candidates. At first glance, these newly identified exoplanets held the promise of groundbreaking revelations. Nevertheless, as subsequent analysis and meticulous examination ensued, it became evident that over half of the initially identified giant exoplanets were deceptive signals masquerading as authentic celestial bodies. They were not genuine discoveries, but rather misleading apparitions. This incident serves as a substantial illustration of the fact that some discoveries cannot be unequivocally regarded as established truths until they are substantiated by a wealth of corroborating data. The NASA Transiting Exoplanet Survey satellite mission, designed to survey expansive regions of the celestial sphere in search of potential exoplanetary candidates, also confronted situations where initially promising observations proved to be less luminous than anticipated. The complexities of light and shadows within our solar system posed challenges to astronomers' capacity to distinguish authentic celestial entities from illusory phenomena. Consequently, extensive efforts were dedicated to the development of instruments capable of precisely identifying celestial objects, enabling researchers to expedite the data analysis process, rather than investing considerable resources in extensive testing to distinguish genuine findings from false positives. The culmination of these endeavors resulted in the creation of the James Webb Space Telescope, JWST, an instrumental marvel poised to revolutionize our ability to scrutinize the cosmos with unprecedented accuracy. The James Webb Space Telescope's Cosmic Odyssey. The James Webb Space Telescope stands as an unparalleled achievement in the realm of space telescopes. Specifically designed for infrared astronomy, its capabilities extend to peering deep into the cosmos, unveiling objects of great faintness, significant age, and remarkable distance. It possesses the unique ability to observe phenomena previously beyond the reach of even the most substantial telescopic instruments. The conception and realization of the JWST resulted from a substantial collaborative effort involving NASA, the European Space Agency, and the Canadian Space Agency. Notably, the telescope boasts a colossal gold-plated beryllium mirror measuring an impressive 6.5 meters, significantly surpassing the dimensions of the Hubble Space Telescope's mirror. This substantial mirror permits the JWST to capture an unprecedented amount of celestial light. Additionally, it conducts its observations primarily in the infrared spectrum, distinguishing it from Hubble's optical capabilities. To facilitate this specialized function, the JWST operates at an extremely low temperature, plummeting to a chilling -223 degrees Celsius. This frigid environment ensures minimal interference with the incoming light it seeks to capture. Currently positioned at a distance of approximately 1.5 million kilometers from Earth, near the Sun-Earth Lagrange Point 2, the JWST enjoys the protection of a sun shield, shielding it from excessive heat. This monumental undertaking demanded an extended period of construction and an investment of approximately $10 billion. Nevertheless, since its successful launch on December 25, 2020, followed by the subsequent commissioning phase, the JWST has consistently demonstrated its extraordinary value. It has embarked on numerous groundbreaking expeditions, unraveling a multitude of previously undiscovered and awe-inspiring phenomena within the cosmos. 500 sizable objects in the Kuiper belt. The favorable operational conditions of the James Webb Space Telescope, facilitated by its space-based positioning, significantly enhance its scientific capabilities, leading the way for pioneering discoveries. In a remarkable achievement, the JWST has recently detected an unexpected phenomenon, the appearance of 500 sizable objects in the Kuiper belt, a region previously thought to be devoid of such occurrences. The Kuiper belt, situated just beyond Neptune's orbit, is an expansive pocket within our solar system, hosting a diverse array of celestial bodies, including comets, asteroids, and remnants from the early stages of solar system formation. Collectively referred to as Kuiper belt objects, these entities possess unique characteristics that offer valuable insights into the composition and nature of this intriguing region. In terms of mass, the Kuiper belt is estimated to be approximately 20 to 200 times more massive than the asteroid belt, located between the orbits of Mars and Jupiter. The asteroid belt serves as an extensive region in interplanetary space, harboring the majority of asteroids in our solar system and preserving a repository of various rocky remnants from the solar system's formation. These asteroids exhibit a wide range of sizes, shapes, and compositions, varying from small rocky fragments to substantial objects spanning hundreds of kilometers in diameter. The orbits of these objects are perpetually influenced by gravitational forces, occasionally resulting in collisions, making the asteroid belt a dynamic and somewhat unpredictable region. It can be categorized into two distinct regions: the inner belt, comprising asteroids orbiting closer to Mars than the 3:1 Kirkwood gap, situated approximately 2.5 astronomical units from the Sun, and the outer belt, housing asteroids closer to Jupiter's orbit. This division is a consequence of gravitational interactions between these asteroids and the massive neighboring planets. Despite its vast expanse, the asteroid belt is relatively sparsely populated, with significant distances between asteroids, often spanning tens of thousands of kilometers. This sparsity facilitates the navigation of unmanned spacecraft through the belt, either as part of extensive missions exploring the outer realms of our solar system, or as dedicated missions focused on studying specific, larger asteroids. These missions provide invaluable data and imagery, shedding light on the composition, structure, and history of these rocky objects. It is important to note, however, that while the asteroid belt covers a substantial area, its overall mass is relatively modest when compared to other celestial bodies. The combined mass of all the asteroids within the belt is estimated to be only about 3% of the mass of Earth's moon. In contrast, when comparing the combined mass of Kuiper belt objects, it is less than 1%. This underscores that while the Kuiper belt contains a significant amount of material, it is notably less massive than our planet. The Kuiper belt's hidden universe of frozen wonders. Kuiper belt objects display a remarkable variety in terms of their size, shape, and composition. They are predominantly composed of frozen volatile substances such as methane, ammonia, and water. These icy components have been preserved in the frigid depths of the Kuiper belt and have remained relatively unchanged since the early days of our solar system. This characteristic sets them apart from their rocky counterparts found in the inner regions of the solar system. One of the most significant findings is the presence of numerous dwarf planets within the Kuiper belt. Some of the most well-known examples include Pluto, Haumea, and Quaoar. These dwarf planets share common characteristics, such as their spherical shape, substantial size, and gravitational dominance over their respective orbits. They serve as important remnants from the early stages of solar system formation, providing insights into the historical development of our solar system. Estimates suggest that there are approximately 35,000 Kuiper belt objects with diameters larger than 62 miles, underscoring the abundance of substantial bodies within this region. Additionally, while we are currently focused on around 500 objects, it is conceivable that there are as many as 100 million smaller and fainter objects measuring 12 miles or less in diameter. These smaller objects, though more challenging to detect, make a significant contribution to the overall population of the Kuiper belt, necessitating extensive research in this area. The intricate dance of resonant Kbos. To further categorize objects in the Kuiper belt, scientists have established two primary classifications: classical and resonant objects. Classical Kuiper belt objects, Kbos, are characterized by stable orbits that remain relatively unaffected by the gravitational pull of Neptune. On the other hand, resonant Kbos have a unique relationship with Neptune, as their orbital periods maintain specific resonance ratios with Neptune's orbital period. This resonance leads to heightened interactions between these objects and Neptune, resulting in the creation of stable orbits. These orbital dynamics provide valuable insights into the intricate gravitational forces shaping the Kuiper belt's dynamics. Understanding the three-dimensional structure of the Kuiper belt offers significant insights into its composition, distribution, and overall nature. While the primary concentration of objects in the Kuiper belt extends up to 10 degrees outside the ecliptic plane, there is also a more diffuse distribution of objects that extends even further. To grasp this phenomenon, it is essential to comprehend the concept of the ecliptic plane. The ecliptic plane represents the flat plane in which most planets, including Earth, orbit the Sun. It serves as a reference point for positioning celestial objects within our solar system. However, the Kuiper belt diverges from this plane, displaying a significant tilt or inclination. This means that the orbital paths of Kuiper belt objects do not adhere to the same plane as the planets, giving them a distinctive spatial orientation rarely observed in our solar system. This distinct characteristic adds to the uniqueness and significance of these objects. The 3D universe beyond Pluto. As mentioned previously, the Kuiper belt primarily consists of celestial objects that extend up to 10 degrees beyond the plane of the solar system, known as the ecliptic. This means that a significant portion of the Kuiper belt's population follows orbits that are tilted relative to the orbits of the planets. These tilted orbits lead to the clustering of objects, creating a dense and compact region within a specific range of angles. In addition to this primary concentration, the Kuiper belt also contains a more scattered distribution of objects that extends much farther. This indicates that beyond the main cluster of objects, there are additional Kbos with a wider range of inclinations, spread out across a larger volume of space. These objects may follow orbits that are more eccentric and inclined, resulting in their broader distribution. The substantial distribution of objects within the Kuiper belt highlights its significant mass within our solar system. It underscores that the Kuiper belt is not merely a flat, disc-like structure. Instead, it represents a three-dimensional expanse of celestial bodies. This expansive nature provides ample space for a diverse range of Kbos to exist, each with its unique orbital characteristics, size, and composition. Tales of icy bodies and solar heat. Determining the composition of Kuiper belt objects presents a distinctive challenge, as their direct observation is often impractical. Consequently, astronomers must employ alternative methodologies to gain insights into their physical characteristics. The current prevailing understanding suggests that Kuiper belt objects are primarily composed of icy materials, predominantly consisting of water, ammonia, and methane. These volatile compounds freeze within the frigid depths of the outer solar system, thereby explaining the icy nature of these celestial bodies. The presence of these volatile substances is confirmed through spectroscopic observations and theoretical models. However, the composition of Kuiper belt objects can vary depending on their distance from the Sun. In the outer reaches of the Kuiper belt, Where objects are more distant from the Sun, icy materials tend to dominate. This region is primarily populated by icy objects and comets that have retained their volatile content due to the extreme cold prevailing in these remote areas. These distant Kuiper belt objects are commonly referred to as cold classical Kuiper belt objects. As one moves closer to the Sun within the Kuiper belt, the composition of objects may change. The specific influence of solar radiation and proximity to the Sun can cause some objects to experience greater thermal effects, leading to a loss of volatile substances and a higher proportion of rocky or less volatile materials. This variation in composition within the Kuiper belt underscores the diverse nature of these objects, with some displaying greater resilience to volatile loss, while others undergo more significant transformations as they approach the Sun. Each object in this entire belt exhibits significant differences from one another, making detailed study a formidable challenge. Fortunately, with the aid of advanced technology such as the James Webb Telescope and other highly sophisticated instruments, researchers are now piecing together this puzzle, which until just a few years ago might have seemed possible only in the realm of science fiction. The evolution of deep-field astronomy. Exploring the farthest reaches of the cosmos to unravel the origins of the first galaxies represents a primary scientific goal of the James Webb Space Telescope. This endeavor is made possible by the remarkable fact that light, over billions of years, traverses the vast expanse of our universe. The telescope essentially offers a glimpse into the past, capturing the light emitted by celestial objects billions of years ago. Astronomers use light years as their unit of measurement, indicating the maximum distance light can travel in a single year. The team's initial graphic emphasized this fundamental concept. On July 11, 2022, U.S. President Joe Biden unveiled an extraordinary deep-field photograph while addressing the nation from the White House. This captivating image was captured by the JWST, recalling a concept first explored by the Hubble Space Telescope when it meticulously examined a small section of the cosmos for an uninterrupted period of 10 days, starting on December 18, 1995. These deep fields have gained recognition for their ability to focus on seemingly minuscule regions of the sky, each comprising only a tiny fraction of the entire celestial canvas. Remarkably, within these minute sections, the Hubble telescope discovered approximately 3,000 previously unknown celestial entities, with the majority being galaxies located billions of light-years away from our perspective. The evolution of galaxies through JWST's lens. A comparatively limited portion of the celestial expanse is scrutinized by the James Webb Space Telescope's Deep Field Initiative, with its primary focus centered upon the distant galaxy cluster designated as SMACS 0723. This specific celestial entity, SMACS 0723, resides at an astonishingly remote distance, situated a staggering 4.6 billion light-years away. What lends particular intrigue to this observation is the profound influence wielded by its potent gravitational field upon galaxies positioned even farther in the celestial backdrop. These background galaxies are subject to considerable distortion, frequently manifesting as expansive arcs in regions of greatest gravitational intensity. In a truly remarkable instance, it was ascertained that light originating from a remote galaxy necessitated an astounding 13.1 billion years to traverse the immense cosmos and eventually reach the JWST's sophisticated telescope. This phenomenon is an outcome of the gradual stretching experienced by the emitted light from these galaxies, a result of the expansion of the universe itself. Given their extraordinary remoteness, the primary target galaxies scrutinized by the JWST have seen their visible light, which emanates from their stellar constituents, extended into the infrared spectrum. Astronomers are now well positioned to facilitate direct comparisons between the data acquired by the JWST and the visible light imagery of nearby galaxies captured by telescopic instruments such as the Hubble and others. The collection of data at these precise wavelengths holds immense promise for yielding vital insights into the evolutionary journey of galaxies throughout cosmic history. illuminating the transformative processes and congregations that have led to the intricate structures that grace the present-day universe. What sets the JWST's initial deep-field image apart is not solely its wealth of discerned galaxies, but also the remarkable expediency with which it was compiled, an accomplishment accomplished in mere hours rather than days. The telescope's gaze, wherever it is directed, inevitably encounters galaxies as an intrinsic characteristic of its observational field. Notably, the sole natural amplifiers of distant celestial objects are the galaxy clusters. Scientists harness the capabilities of the JWST to photograph a pair of galaxies designated as VV191. This endeavor enables them to investigate how the light emanating from one galaxy transforms as it traverses through the other. The outcomes stemming from this research endeavor are anticipated to unveil intricate details concerning the presence of cosmic dust within the intervening galaxy. A close-up of Stéphan's quintet's celestial ballet. Galaxies and black holes have been a subject of keen interest since the telescope first captured its initial images. Among these celestial entities, there exists a closely knit assembly recognized as Stéphan's quintet, comprising 4 galaxies that engage in an intricate gravitational dance owing to their proximity. The 5th galaxy in this assemblage may appear to be nearby, but in reality it lies much closer to our vantage point, coincidentally aligning with the others within our line of sight. Together, these 4 interacting galaxies serve as a unique laboratory for astronomers to investigate the dynamics of galactic interactions and eventual mergers. Such mergers were likely commonplace in the early universe and played a pivotal role in the formation of the vast galactic structures that we currently observe. Additionally, they are believed to be intimately linked to the growth of supermassive black holes, each situated at the center of its respective galaxy. The JWST conducted observations of Stéphan's quintet employing its near-camera and mid-infrared instrument sensors. Of particular note, the images captured by MIRI surprised astronomers by unveiling previously unforeseen aspects of these galaxies. Now, it's time for today's subscriber pick. The universe continues to astound us as the James Webb Space Telescope just detected 755 unidentified objects arriving from another solar system. This discovery has sent shockwaves through the scientific community, leaving us with more questions than answers. What are these enigmatic interstellar visitors, and what could their arrival mean for our understanding of the universe? The telescope's keen eye has opened a door to an entirely new realm of cosmic exploration. Imagine the possibilities. Could these celestial travelers be remnants of a distant, ancient civilization, or perhaps the seeds of life from another corner of the cosmos? What mysteries might they hold? And what can we learn from their presence in our cosmic neighborhood? As we eagerly await further data and analysis, one thing is certain: the universe continues to be a source of unfathomable surprises, challenging our understanding and beckoning us to explore its endless wonders. The James Webb Space Telescope has once again proven itself as an invaluable tool in unraveling the secrets of the cosmos. And with each discovery, we move one step closer to comprehending the vastness of the universe and our place within it. Let us know what you think about this discovery in the comments below. Unveiling the phantom Galaxy M74. A notable accomplishment of the MIRI instrument pertains to its investigation of the phantom Galaxy M74. This spiral galaxy is positioned at a distance of 32 million light-years from Earth and presents itself nearly head-on to our observation. The distinctive spiral arms, which serve as defining features of spiral galaxies, have long captivated the interest of astronomers. Nonetheless, until this juncture, no one had the privilege of perceiving them with such exceptional clarity. For the first time, we are afforded a comprehensive view of the spiral arms within this galaxy, wherein active star formation processes are visibly extending towards the core of the galaxy. Collaborative endeavors hold paramount importance as we aspire to amalgamate the newfound insights derived from the telescope's observations with the data harnessed by pre-existing observatories. This collaborative initiative promises to deepen our comprehension of the celestial entities under scrutiny and, ideally, pave the way for groundbreaking discoveries. A prominent advantage inherent to infrared astronomy, a speciality of the JWST, lies in its capacity to peer into the recesses of star-forming regions with exceptional efficacy. This advantage stems from the lengthier wavelengths characteristic of the infrared spectrum, which exhibit reduced susceptibility to interference from dust, molecules, and atoms. Consequently, these longer wavelengths render objects that typically obscure our view of stellar nurseries virtually transparent. This distinctive capability empowers us to explore the life cycle of stars with heightened precision. An additional image captured by the telescope has provided us with a closer view of CAM's observation of the star-forming region known as NGC 3324, which is situated approximately 7,500 light-years away within the Carina Nebula. The Carina Nebula, predominantly consisting of gas and dust that has been sculpted by the radiant influence of stars, offers a captivating panorama reminiscent of a terrestrial landscape. What is truly remarkable is the utilization of infrared technology to peer into this once-concealed domain, now unveiled in all its splendid grandeur. Initially christened as the Cosmic Cliffs upon its discovery, this expansive assembly of gaseous precipices bore a semblance to a mountainous formation. In actuality, it demarcated the periphery of a substantial cavity, gradually eroded by the intense ultraviolet radiation emanating from youthful stars. From red giants to white dwarfs. In the later stages of a star's life cycle, the James Webb Space Telescope has provided valuable insights into the processes governing stellar evolution. Similar to our Sun, stars of a sun-like nature undergo a remarkable transformation. They first expand into red giants before eventually contracting into white dwarfs, ultimately transforming into stellar remnants. During this contraction phase, they shed their outer layers, giving rise to what is commonly referred to as a planetary nebula, though this term only partially encapsulates the true essence of this phenomenon. The JWST's imagery of the Southern Ring Nebula provides a vivid depiction of this captivating process. The star undergoes a cyclical pattern of expelling layers of matter from its outer shell throughout thousands of years as it progresses towards becoming a white dwarf. Subsequently, the star's remaining core experiences compression and an increase in temperature, initiating a fresh phase of energy generation and pulsations. Each pulsation event results in the expulsion of another layer of material. This cyclic process persists indefinitely until the available material becomes insufficient to sustain the core's pressure and instigate nuclear fusion. At this juncture, the star attains the status of a white dwarf. Interestingly, this fate mirrors the destiny that awaits our own Sun in approximately 4.5 billion years. James Webb's quest for exoplanetary secrets. One of the central objectives of the James Webb Space Telescope is to observe planets in various phases of development, ranging from nascent celestial bodies to more mature planets that encircle distant stars. The telescope's exceptional infrared capabilities empower it to penetrate the shrouds of gas and dust enshrouding star-forming regions, allowing us to witness the emergence of planets around newly born stars. This capability also enables scientists to dissect the chemical compositions of a planet's atmosphere independently from the elements present in the star it orbits. To accomplish this, astronomers precisely align the JWST with a star where they anticipate a planetary transit, wherein the planet traverses directly in front of the star from our point of view. The telescope captures images of both the star and the planet as the latter crosses in front of the former, thereby unveiling the composition of the planet's atmosphere. For example, in the instance of WASP 39b, a celestial body located approximately 700 light-years distant, the JWST successfully identified the presence of carbon dioxide within its atmosphere. This momentous observation marked the inaugural identification of carbon dioxide on another celestial body. Additionally, the JWST detected other substances such as water vapor, potassium, sodium, and carbon monoxide within the planet's atmosphere, many of which had never before been detected in the atmospheres of exoplanets. The TRAPPIST-1 system has generated significant anticipation among space enthusiasts. TRAPPIST-1, a red dwarf star, is orbited by 7 Earth-sized planets. What is particularly intriguing is that several of these planets reside within the habitable zone, where conditions conducive to life may potentially exist. If we were to pinpoint a location with the highest likelihood of hosting life beyond Earth, this system would emerge as a compelling candidate. The telescope is methodically investigating these planets, meticulously scrutinizing their atmospheres or, in certain instances, the absence of atmospheres. In its inaugural year, the Webb telescope has managed to scrutinize only 2 of these planets. The first one, TRAPPIST-1b, resembles a supermercury, and, as anticipated, it lacks an atmosphere. However, the second planet, TRAPPIST-1c, has piqued the interest of astronomers. They held high expectations for this planet, hoping it might resemble a super-Venus. Unfortunately, akin to its counterpart, it also lacks an atmosphere. As things stand, we have 2 rocky, airless worlds orbiting around TRAPPIST-1, with 5 more yet to be explored. Gravitational lensing superpower. The James Webb Space Telescope possesses formidable capabilities in its own right, but its potential is greatly enhanced when it synergizes with a gravitational lens. This extraordinary arrangement leverages the gravitational influence of an entire assemblage of galaxies to function as a naturally occurring lens, facilitating considerably more precise observations of celestial entities situated beyond this focal point. These observations unveil intricate insights into the constituent elements of these distant galaxies that would otherwise elude detection through the intrinsic capacities of the telescope. Additionally, this configuration bestows supplementary benefits. In a particularly noteworthy occurrence, the James Webb Space Telescope detected numerous iterations of a single supernova event within a galaxy. This phenomenon materializes due to the phenomenon of light from the supernova following distinct trajectories around the gravitational lens engendered by the galaxy cluster. Consequently, astronomers were able to observe the same type of supernova event occurring multiple times, contingent upon the various pathways taken by the light as it circumnavigated the intervening galaxy. The sheer potential entailed in employing the gravitational pull exerted by a galaxy cluster as a natural telescope is undeniably remarkable. It allows us to scrutinize celestial objects with a level of clarity exceeding that which would be attainable solely through the utilization of the telescope's intrinsic capabilities. As we persist in grappling with the enigma of dark matter, it is nothing short of astonishing that we can harness it as an instrument for scientific exploration. Unveiling cosmic collisions and starlight brilliance. This image bears an immediate and unmistakable resemblance to the work of the James Webb Space Telescope. One can readily discern the characteristic hexagonal star shape, a direct consequence of the hexagonal mirrors employed in the telescope's construction. These mirrors play a pivotal role in producing this distinct star-like configuration when capturing luminous celestial objects. Upon closer examination, one will observe the presence of 2 additional lines stemming from the supports that uphold the secondary mirror of the James Webb Space Telescope. In this specific illustration, we are presented with a celestial entity identified as ARP-220, a product of the collision between 2 galaxies. This collision results in an extraordinarily intense luminosity, to the extent that it begins to challenge the sensitivity of the telescope's sensors. In the visible light spectrum, this image reveals the captivating union of these 2 galaxies, a spectacle that holds one's attention. However, when observed through the infrared spectrum, it radiates with the brilliance equivalent to that of 1 trillion suns, which is approximately 100 times more radiant than our own Milky Way galaxy. This represents the initial phase in the gradual transformation of these colossal galactic entities. In due course, these galaxies will evolve into massive elliptical galaxies akin to M87. These behemoths emerge as a consequence of numerous galactic collisions over time, as they assimilate smaller dwarf galaxies situated in their proximity. Once these giants have absorbed all available smaller galaxies, they will reach a state predominantly comprised of a profusion of stars. Over time, these stars will gradually shift towards a redder hue, marking the progression of their cosmic evolution. Do you think the discovery of advanced extraterrestrial civilizations is imminent with the advancements in space technology? Share your opinion in the comments below.